discuss about the critical speed of shaft carrying single rotor with damping. Now, for with damping case, the all parameters will be same, but due to existence of damping, there will be the damping force, and the damping force will be equal to the C omega y, which means the C is the damping coefficient, omega is our angular velocity, and y is our deflection. The centrifugal force, suppose that this CG is over here, the centrifugal force acting will be in this direction, which will be the m omega square a, because over here from center the distance is a. So, and the restoring force will be acting in this direction, which will be equal to k into y, and the damping force, suppose the rotation is in this direction, the damping force will be in the opposite direction, which will be the c omega y. Now we have to resolve the due to damping force, the point O, S and G no longer on the same axis because of damping force. They will not be in the same axis, and this is the cross section we can see over here. This is our centrifugal force, and this will be our Cm omega y. This is our damping force, and this is the Kx, which is the restoring force, or which is called as the spring or stiffness force, Ky. So here we can see this will make psi angle, and this will make a phi angle, G and S. Here there will be the C omega y, and this will be the m omega square a, and kx will be ky in this direction, k into y. So there are two components of this. First one is cos component and another one is sine component. Same way over here we will get the eccentricity E, eccentricity which means the center of rotor, and CG, both are in displaced condition. S and G, the distance between both center of rotor. This is our rotor center, and this is our CG. This is called as eccentricity. So the cos and sine component will be this. Same way for A, there will be the A cos psi and A sin psi. Now we have to resolve all the horizontal forces which are acting and vertical forces. So as you can see, the horizontal forces is m omega square a cos phi and ky, and vertical force is m omega square a sin psi and c omega y. So what will happen by resolving the horizontal force? Because we will get the sigma fx and sigma fy. Now as we can see, the cos m omega square a acts in positive direction while ky acts in negative direction, so this will be taken as minus. Same way for vertical forces, this will be in the upward direction, and c c omega y, which is our damping force which acts in opposite direction. So this will be considered as negative, this will be considered as negative. So that we can see in this equation number A and B, we can see. Now from this figure, A sin omega, A sin phi will be equal to E sin phi, and A cos psi will be equal to Y plus E cos psi. These two we can see in this equations. So we put the value in the above equations, these two equations. We put the value of A sin psi in this equation and A cos psi in this equation. We will get the value of E cos psi and E psi we will get by resolving this equation in terms of y, e and phi, which are non terms. So we can make the y as, we can find the deflection from this equation. And on substituting value in the second equation, we will get the c omega y equal to m omega square. Here first we put the value of A cos phi in this equation, and in the second equation we will put the value of A sin phi, and we will get this equation number F and E. So taking the ratio of both equation, we will get the sin phi upon cos phi, which is equal to the tan phi. So this will be tan phi, and as we know that the c omega by k minus m omega square, which means if we divide by k, we will get this 2 zeta omega by omega n upon 1 minus omega upon omega n square. So we can find the angle phi. Now we can write here omega n is equal to omega c for critical speed, and this is the equation gives the phase angle between the eccentricity line and deflection line here, and the angle by which the deflection lags. This the phi. Now we will discuss about the variations. Here we can see from there is a phi, and this is the horizontal and vertical side, and this is the hypotenuse. So we will get the sine is equal to opposite upon hypotenuse. Same way we can find the cos, which is equal to adjacent upon hypotenuse. Same way, and we can find the deflection y. Now from this equation, here it is given that the deflection of geometric center of rotor from initial undeflected position for whirling of shaft are same as that of the force damped vibration with rotating and reciprocating unbalance in case of force damped vibration due to rotating or reciprocating unbalance. The unbalance was in terms of small mo, whereas in this case the unbalance is defined in terms of total mass m with eccentricity e. So we will discuss the various possible phase angle. Here the first phase angle is when the angular speed is lower than the omega n and phi is equal to 0, which is heavy side out. So this will be the first case when omega is less than omega n. Same way here it is given for the omega less than omega n, which means the angle phi is between 0 to 90 for heavy sideways. Same way for omega by omega n is equal to way which is considered over here, and phi angle is 90 degree for omega greater than omega n, and which is between 90 and 180. And last one is omega is very greater than omega n, y is equal to minus e, and phi is equal to 180 degree for light side out rotors about its CG. So these are the various possible phase angles we can see. So this is it for today's lecture. Thank you very much for watching.